This is the second section of the integration chapter, and it's integrating functions of the form f and then in brackets ax plus b. So it's where we're trying to integrate something which is a function of ax plus b dx. Now I actually call this the reverse chain rule. They don't call it that in the book, but I do, so I reckon I'm right and the book is wrong. And you'll know from the normal chain rule there were two steps, weren't there? So when we used the chain rule to differentiate, what were the two things we did? Well, we differentiated the outside. I'll just write differentiated the outside, and then we multiplied by the inside differentiated. Okay, so an example might be if I wanted to differentiate sine of 4x minus 3, that was y, then dy dx, well, if I differentiate the outside, that becomes cos. The inside of the bracket doesn't change, and then I multiply by the inside differentiate, so times by 4, so you'd end up with 4 cos 4x minus 3. Now if I'm going to integrate that, so if I integrate my answer, I should get back to this, and the way I'm going to get back to that is by reversing the two steps here. So where I've got differentiating the outside, I reverse it, I integrate the outside. Yeah, so this cos integrated would become sine. That's step number one. The second thing we do is we divide by the inside differentiated. Here we multiplied by the inside differentiated, but now we divide by the inside differentiated. So if I were integrating this, I would divide by this differentiated, I would divide by 4, and that will get me back to here. Now notice with this reverse chain rule, which I'll highlight here, part of the method of integration actually requires you to differentiate, which you might think is a bit odd, but we need to differentiate in the process of integration. But there's one sort of caveat, one sort of exception, and that is that this reverse chain rule only works when the inside is linear. Okay, so what's in the brackets here, this must be linear, and it actually is because you say x plus b, for the what I'm calling the reverse chain rule to work. Why? Let's do an example where the inside isn't linear and see what happens. So let's say that I had y equals, so we're working out why this doesn't work. Y equals, let's go for cos 2x squared minus 1, and let's say we wanted to integrate that, so we're not going to have y equals, we're going to try and integrate that using the reverse chain rule. So the first thing that we do is we integrate the outside. Cos integrated is sine. Okay, now just like the normal chain rule, the inside of the bracket does not change, and the second part of the reverse chain rule is to divide by the inside differentiated. Now the inside differentiated will be 4x. So what do I end up with? I end up with 1 over 4x sine 2x squared. Now, if I were checking to see if this works, I would have to differentiate this. Of course, we have plus c. I should get back to that if I differentiate. Yeah, if I differentiated this 1 over 4x sine 2x squared minus 1, I should get back to that. But I would not differentiate this using the chain rule. I would differentiate this using the product rule. So if I would differentiate this using the product rule, I can't say that I'm going to reverse that by doing the chain rule. Yeah, if the inside of this bracket isn't linear, like it was here, then you end up with a function times another function which you would have used the product rule on. So maybe it might be helpful to do it like a diagram like this. So we've got some sort of function over here, and we use the let's say we're differentiating going this way, and let's say that to differentiate I use the product rule. So to get back there, I can't use the reverse chain rule. Yeah, it doesn't work. So the inside of the bracket must be linear. If it's non-linear, you end up with a product, and if you differentiate and go back to where you started, you should get back to where you start, but you won't, because you would have used the product rule here to differentiate this, not the chain rule. So if you use the chain rule one way, you've got to use it back the other way. If I use the product rule one way, I can't reverse it by using the chain rule or reverse chain rule. That doesn't work. On to some examples. Right, now I think in all of these the inside of the bracket is linear, and we've got our list of integrals here, including the ones that we should be memorizing. So so the steps are to integrate the outside, so cos becomes sine. Then we divide by the inside differentiated, so the inside differentiated is 2, so we divide by 2. So you might want to write it as half sine 2x plus 3. B. Right, now this time the inside is this 4x plus 1. So we integrate the outside, so e integrated is e, and then we divide by the inside differentiated. The inside differentiated is 4, so we divide by 4. So we have a quarter e to the 4x plus 1. So maybe putting the inside in brackets sometimes help. And then the last one, c. So we've got sec squared. Now sec squared is here on our list of integrals. That's the one we'd probably need to look up. And the inside is 3x on this. Yeah, so putting the brackets helps. So sec squared integrated is going to be tan. So we integrate the outside, so you end up with tan 3x. Then you divide by the inside differentiated, which is 3, and we can write that as 1/3 tan 3x. Now all of these should have plus c. Now to do part A, I'm actually going to be considering what happens when I integrate 1 over x. And I'm going to use that to help me, so I'm just going to put it over here because it looks similar to 1 over x, and I know 1 over x is going to give me log x plus c. So why not, let's try log of 3x plus 2. So actually on this one, when you integrate the outside, 1 over the inside becomes log of the inside. So the outside is basically the 1 over, and that becomes log. So it becomes log of 3x plus 2 Yeah, so that's, you think of whatever's down here, this linear part, as the inside, and then you almost need to think of like the 1 over part as the outside, and then when you integrate the outside, that will become log, basically, of the bottom, log of the inside, yeah, which is what we're doing here. So integrate the outside, 1 over something becomes log over the something, divided by the inside differentiate, so you divide by 3, so we end up with 1/3 log 3x plus 2. Next one here, b, so we integrate the outside, so the power will become 5, and we'll divide by 5, so I'll write a fifth. Inside of the bracket doesn't change. We divide by the inside differentiated, so we divide by 2, so 1/5 will become 1/10, and then 2x plus 3 to the power 5, and plus c plus c. Keep forgetting to put my plus c's in. Right, you should now be able to do exercise 11b on pages 297 to 298. Now you could, if you want, remember a whole load of rules about I don't know, things like if you're trying to integrate 1 over ax plus b dx, that's going to be 1 over a log ax plus b plus c. But I think it's a waste of time. You don't want to remember all of these rules, because like you have to remember loads of them. Things like, okay, you want to integrate cos of ax plus b, so that's going to be 1 over a sine ax plus b plus c. Yeah, I wouldn't spend your time remembering all of those different rules, because there's going to be loads of them. I would spend your time remembering the process so you can apply it to any integral. Okay.